In this video, we want to look at some transform pairs, which is a bit of a review over the Laplace transform, but also I want to look at some of these transform pairs with respect to thinking about how we're going to inverse transform. So let's go through this brief set of transform pairs and examples taken from your textbook, and we'll talk about, actually I believe this is taken from another textbook just to give you a slightly different presentation. So we'll talk about the transform pairs both as far as the Laplace transform goes in way of review, and then also starting to look at, as we take the inverse transform, what kinds of things we should expect. So I just have here repeated the definition of the Laplace transform. You notice this source does not show the squiggly brackets like your textbook does. I always use the squiggly brackets. I like those. And you see the integral transform then, and a reminder that S is a complex variable given by sigma plus j omega. So the first transform pair is the simple impulse function. And so when you take the impulse function and you insert it, let me go to screen show, and you insert it into the transform definition. So this is your transform integral where del of t is your f of t. And so you insert this. Well, now what happens is you use the sifting theorem of the impulse function. And so if you recall, the sifting theorem means if you have del of t minus a, whatever a is, you substitute it into the function that it's being integrated with. So in this case, that's the Laplace transform function, e to the minus st. You substitute a 0, and you're going to get a 1 out of that. So what I want to point out is that this is your function in the S domain. So if you have an S domain function that is a 1 or a constant, and you're trying to take the inverse transform of that, that is going to generate impulse functions. Now the step function u of t, you basically once again substitute into the integral. You do the integration, and you end up with, in the S domain, 1 over s. So if in the S domain your function of s has a 1 over s term, that is going to inverse transform into a step function. K here is e to the minus at u of t. If we transform that, we come up with the following form, 1 over s plus a, which says that if in the Laplace domain your f of s is of this form, 1 over s plus a, when you inverse transform it, that's going to be a step function, but it's going to be multiplied by e to the minus at. So that's what gives us this form in the Laplace domain. Okay, here's the sinusoidal function. Now this is one of those tricks that I was talking about, how you take a function of infinite extent and you actually create its Laplace transform. So in order to do that, we've taken the sine function and we've used Euler's expression, and then from Euler's expression you can then take the transform, do some manipulation, and you end up with something of this form. So what I want to focus here on is the denominator, because cosine has the same form except there's an s in the numerator. But if you look, this s squared plus omega squared, this can't be factored further into real roots. So anytime in the Laplace domain you have something of the form s squared plus a constant in the denominator, you know that that's going to transform into a sinusoid or a cosine. Okay, this is an important property, and it's going to be very important in taking the inverse transform. It's basically the property of linearity. So if we have functions f1 and f2 and they're added and multiplied by some constant, that just says we can take the transform of each one independently and still multiply by the same constant. So that's the process of linearity. Now that's important because one of the things we're going to have to do in the S domain is we're going to have to use partial fraction expansion in order to get us to a point where we have a function in this form. And then, so using the property of linearity to take the inverse transform is going to be important there. Okay, the time shift property, basically what this says, if in the Laplace domain, it says in the time domain, if I have a function and it and its step function multiplier are both time shifted by some amount a, that transforms into whatever the time function would have transformed into times this exponential e to the minus as. So if in the s domain I have some function of s and it's multiplied by e to the minus as, the thing to do there is to temporarily ignore the e to the minus as. Transform the function in the s domain back to the time domain, and then realize that the e to the minus as part is going to introduce this time shift a. So that's what we're going to do there and why this is useful. Okay, furthermore, if you have in the Laplace domain a function that is a function of s plus a, that transforms back into multiplication in the time domain by e to the minus at. Those are almost dual properties, except going back to the time domain, you have a negative exponent as opposed to a positive one. Okay, time differentiation is not used that much in taking the inverse transform, but it's important to talk about because one of the ways we end up with a function in the s domain anyway in applications is that we have some integral differential equation that's defined our system. So given that we have a system defined by an integral differential equation, we can basically transform that to the Laplace domain using this property of derivatives. And so if you have the nth derivative of f, that's going to generate an algebraic function in s. So this algebraic function, much easier to solve and inverse transform. So this is kind of, one of the motivating factors for why we would end up with this function in the s domain in the first place. And once again, sometimes if you have a function in the s domain and it's divided by s, you can actually get the inverse transform by taking the inverse transform of the f of s term and then taking care of the 1 over s by performing integration in the time domain. So we'll see some examples of most of these. I don't want to talk too much about frequency differentiation because in the inverse transform realm, it's not particularly useful. It can be very useful in the time domain. So if you have some function f of t and it's multiplied by t, that's basically just take the transform of f of t, you'll get f of s, take its derivative, multiply by -1, and that'll take care of the t in the time domain. Okay, there are two important theorems before we talk about the inverse transform. And one of the reasons to show these is that you can do certain things in the s domain without having to take the inverse transform. The first is the initial value theorem, and this one is not particularly useful in electrical engineering because we often are dealing with problems that have initial conditions that would occur at 0 minus. But basically what this says is if you want to know what your function was at 0 plus, the instant after 0, then you take the function in the Laplace domain, you multiply it by s, and then you take the limit as s goes to infinity. So this is referred to as the initial value theorem. The one that's much more commonly used in electrical engineering is the final value theorem, and one of its main applications is in either control systems or in circuits to try to figure out as time goes to infinity, when the transient effects have gone away, what is the final value of whatever parameter it is you're measuring. So in the time domain, you would basically take your function and let it go to infinity, let t go to infinity, and evaluate the function. In the s domain, you have this function f of s. What you can do is multiply that by s and then take the limit as s goes to 0. It's often easier to take limits as something approaches 0 than it is as it approaches infinity. The value that you get out of this limit will be the final value or the value in the time domain of the function as t goes to infinity. So here are a couple of examples. Here's a function e to the minus 2t sine of 5t. You can transform that using the tables and get the following form. And then in order to apply the final value theorem, we take this function, we multiply by s, we get the following function, we take the limit of that as s goes to 0, and we get 0, which you can say was actually obvious by looking at this time domain function in the first place. So that's the final value theorem. Once again, a brief review. This is from a different source, so I wanted you to have it in your notes. This is Laplace transform pairs. One table and another table of properties of the Laplace transform. The one thing that you need to remember is that, of course, we are always assuming that this f of t, this is a single-sided transform, so we're always assuming everything here, it's implied that it's multiplied by u of t, or that it's only valid for t greater than or equal to 0. So, and here is the properties of the Laplace transform, kind of a summary, the same thing that your book would call operational transforms, just giving you a different table. So now that we've looked at these tables from the perspective of how to take the inverse transform, let me go back to this table one more time before we end the video, and let me say that the goal in taking the inverse transform, no one integrates to do an inverse transform. What people do is you try to get your f of s to look like one of these functions in the right-hand side of this table. So if we can do that, then we can inverse transform using the table directly. So the focus on taking the inverse transform is on how to get your function of s to look like one of these.